these will actually be in the form of a hard copy, so it won't be electronically distributed. So if everything goes well, Chris will distribute them on Friday. Okay, so you have that to look over. We've not yet marked the first assignment, but we will do that next week. So hopefully you'll get sort of feedback from that fairly shortly. Just to bear in mind, I don't expect tremendously detailed feedback from this. It will really rather be sort of right or wrong sort of answers, and we will give you what we believe are sort of model answers, rather than saying where we think you went right or wrong. We just say this is kind of what we think you should have done, and it's very time consuming to go through all of the details of your solutions and work out what exactly you did wrong. Okay, any other questions about sort of where we are, admin, blah blah blah? Everything okay? You coping with the course workload? Okay? Yeah? Not too bad? Good?
A bit less.
A bit less? A little bit better? Oh, well, yeah, I guess that's but if it's survivable, then it's okay. Alright, so we're going to talk about decision theory today. I'm not quite sure if we managed to talk about anything else, but we'll try to for this topic. This topic is a little bit more difficult. So to give you the kind of bigger picture, well, what have we been doing and where are we going to? Well, we've been talking about some basic probabilities, structured probability distributions, graphical models, and we've been discussing how to do inference efficiently in those graphical models. Okay, so we sort of talked about relief networks, we talked about Markov networks, and we talked about some other representations of these things like vector graphs, and then we showed how in the singly connected case we can do certain kinds of inference efficiently. And for the multiply connected case, there exists this algorithm, the junction tree algorithm, which, if you're stuck, you can basically use that to solve your inference problem. So though bearing in mind it's not necessarily the most efficient algorithm which would ever exist for a particular problem. Now we're going to move on to is another form of inference, namely when we want to have some decision variables in the inference. And then when we finish this today, we'll be done with the sort of inference part of the program. And we'll move on to learning, so how to learn the parameters of probability distribution. This is where the machine learning connection will come in. Okay. So this is just to hang in there. So the second half of the course will be about learning all the parameters of these distributions. Okay, so decision theory. We're going to talk about the concept of utility or loss, and we're going to talk about what would you do, how do you take decisions under uncertainty, not knowing for sure what's going to happen in the future. So one approach is to sort of think about what's likely to happen and what your likely costs or benefits or utility is going to be in the future, subject to taking a particular decision. So let's look at an example here. So you're going to be tossing a coin, heads or tails, and the coin is fair, so it comes with heads and tails equally likely. And so the game is that if you take this bet on, and let's say you win the coin toss bet, so you guess correctly whether it's heads or tails, you're going to get £100. But if you bet and you lose, you're going to lose £200. Okay. So if you don't bet, we decide not to play this game. It doesn't cost you anything. So the question is, should you play this game? Because you don't. The point here is you don't know. Obviously, if you knew you win, then you of course you would play the game. But because you don't know whether or not you're going to win, so one sort of approach to rationalize about whether or not you take this bet on is to say, well, how much would I expect to gain if I sort of take this game? But one way to set this up is to say, well, okay, there's a utility which has got a function of two variables. So if I win and I bet, then I get £100. That's the utility. If I win, if I lose on a bet, I lose £200. In the case that I don't bet, whether or not it's win or lose, it doesn't cost me anything. Right? So what is the expected utility if you bet? Okay, well, it's a probability winning times by the utility of winning, plus probability of losing times by the utility of losing, given that you bet. Okay. So this is, you work these sums out and you get minus 50. Okay, and utility of no bet similarly would be probability of winning, utility of winning and no bet. No bet, but they're both 0. So utility is 0 and there's no bet, so that's 0. So based upon this, you would say, well, look, the utility of betting is minus 50, and no betting is 0, so actually, rationally, I should not bet because I'm going to lose less expectation than I would if I were to bet. Okay, so based upon this, you would then say, okay, you would not do that. So this is a kind of, if you like, way of rationalizing decisions theory, decisions or uncertainty. This goes back to people like Savage in the 1950s. So this is kind of maybe one way to do it. I guess there are other frameworks for taking decisions and uncertainty, but this is the one we're going to use here. Okay, so let's look at another kind of example. So you've got £1 million in your bank account. That's quite a fortunately wealthy person. So somebody again asks you whether or not you'd like to take another bet, a coin tossing bet. Okay. But the stakes are a bit higher in this case. So if you decide to bet this time and you win, you're going to become a billionaire. Okay, so in other words, 10 to the power 9 pounds in your bank account. That sounds great. The flip side is, if you lose, you're going to take all of your money nearly, and you're going to be left with £1,000 in your bank account. So you're a millionaire, and you can play this coin game. If you win, you become a billionaire. If you lose, become a what is for £1,000. Actually, this is terrible. This English it doesn't make any sense. Billionaire in English is nonsense. It's categorization. But anyway, we should go back to the old European way of doing these numbers. So let's work out whether or not it's it's rational to bet in this game or not. So we do this. Utility of betting. Well, if you win, you get £1 billion. Probability of half. If you lose, you're left at the end with £1,000. Probability of half. So the expected amount of money you're going to get is just over £500 million. It's pretty good. Utility of no betting. Well, if you don't bet, we're not going to change your bank account. So you stay the same. So clearly, it's much, much better, according to this, to bet than not bet. But then ask yourself, if you're a millionaire, of course it depends on how easy you got this £1 million. Let's imagine that you worked very hard to get this £1 million, and are you're already quite a wealthy person. Are you willing to risk throwing it all away, pretty much, just for the chance of becoming a billionaire? I don't think there are many people in the world who would take on this bet rationally, but they would not willingly take on this bet. So this is the point where mathematics sort of has to take a back seat. It says, well, that's fine, but clearly what this sort of suggests is that the utility of the human concept of the utility of money is not a simple linear function of the quantity of money that you have. So in other words, the utility of being let's say, a billionaire, it's higher than the utility of being a millionaire, but it's not that much higher. Similarly, the utility of being a millionaire compared to only having £1,000 is higher, of course, but it's a lot higher. So there's a kind of trade-off. Your utility is kind of slowing down as you get wealthier. Surely, it's not sort of it's kind of asymptoting, if you like, to some kind of I'm the richest person in the world, and there's no point trying to be richer than Bill Gates because it it doesn't matter, right? So that's kind of more a psychological effect. So there's this kind of concept in psychology that there's a non-linear dependence really between the quantity of money and the sort of the observed perceived value of the money. So one way to think about this is that some of this is my personal feeling now. I mean, this is nothing really from the textbooks, I think, but I think that somehow whether or not you feel that you're doing well economically, it's really a function of how much money you have compared to other people. It's not an absolute thing. I think it's really people think about these things in a kind of a relative sense. So in other words, if you said, well, look, I'm in a job where 99% of people have a higher salary than me, you'd be kind of like, well, unless it's something, very, there are other reasons, that you feel that you're doing a socially good service, etc. But, generally people are going to feel pretty pissed off about their salary, right? On the other hand, if, you say, well, there's only 1% of people who've got a higher salary than me, 99% of people are worse off than me in terms of their salary, then you're going to feel pretty good, right? So, even if there's a few people that have got more cash than you, it won't really affect you that much, right? So in some sense, you could say, if you were to randomly sample, say, a person's, so you've got a particular salary, and you randomly sample from the distribution of salaries which are existing in your area, and you say, well, the probability that a randomly sampled person will have a higher salary than me, that sort of would make you feel bad. So the higher that probability is, then the worse off you're going to feel. And that probability, the probability that somebody in the population is going to have a higher salary than yours, is just given by the integral over the density of salaries of that requirement. This is the definition of the cumulative probability. So I'll show you a picture in a minute. So if you think about that, what's going to happen is the cumulative probability is going to have actually this characteristic asymptoting performance. So maybe I'll show you the demo. So what I'm plotting here on the left is this is just calculation we did before. In the linear case of the utilities, it's a linear function of the quantity of money we've got. So you find that it's much better to bet than not to bet. Now this is some wealth distribution in the population. I just made this up. Actually, what I'm saying here is that there are 10 bins, and these correspond to your salary. Okay, so this is kind of the money that you have. So it doesn't really matter what this scale is. It's could be say hundreds of thousands of pounds. So most people have got a kind of average salary. They're somewhere in the middle. There are some poor people, a small number of poor people, and there are a small number of wealthy people. So the probability, if you were to say have a salary here, what's the probability that a randomly chosen person in the population is going to have a salary higher than that is given by, or say lower than that, is given by this problem here, right? This is the cumulative density of this thing here. So probability, if I've got a salary of 7, that there's going to be the people are going to have a worse salary than me is given by 0.1 is 0.8. Okay. So this is the kind of the characteristic sort of taming off behavior I was talking about. So if you use that now as this becomes your utility function. So this is your input, and this is the corresponding utility. It's a non-linear function now. What do you get? Well, you find out in this case that the utility of betting for this particular example is actually worse than the utility of not betting. Again, it doesn't really matter what these levels are here. These are some arbitrary. This is that's the point, right? So, and I think that corresponds more to the reality of what goes on in practice. Okay, so that's a little bit of psychology, I guess, more than that. But it's kind of interesting. I think that's the way somehow things are going. So we want to, though, put this kind of decision theory framework now in kind of more structured scenarios. So let's think about a slightly more complex example. So you're going to try to organize a party, and the problem is that, well, let's say this is a garden party, so it's going to go ahead outdoors somewhere, and the problem is that if it rains, nobody's going to come to your garden party, so you're not going to make any money. On the other hand, if you decide to go ahead with the party and it doesn't rain, that's good, right? So people will come and they'll give you some money. On the other hand, if you decide not to go ahead with the garden party, then you could say, well, that's fine, because if I don't go ahead with the party, I can go and do something else. So it's reasonable for something else. So we could set this up in the following way. You could say, well, the utility probability that it rains, say, is 0.6. Probability it doesn't rain is 0.4. Utility, if I go ahead with the party and it rains, that's really bad. I'll lose £100. If I go ahead with the party and it doesn't rain, that's good. I'll gain £500. Say, if I don't go ahead with the party and it rains, that's okay, let's say. And if there's no party and it doesn't rain, that's not so bad, because I can go and do something else. The question is, should you go ahead with the party? Okay, under again this expected utility setup. So what we could do is say, well, look, let's figure out what's the expected utility going ahead with the party. Well, rain is the only unknown quantity here. We don't know when it's going to rain. So let's compute the expected utility of the rain. So again, these are the two states of rain here. Get 140. Similarly, you could say, well, what happens if we don't go ahead with the party? The expected utility, working it out, is 20. So it seems to be a good idea to go ahead with the party. Okay, so that's nice. There's another way to write this down. You say, well, actually, I could formalize this in terms of a kind of tree of decisions. So I could say, well, let's say, so what's going on here is that there's a decision node here, whether or not to go ahead with the party or not, and you could go yes or no, and then the question is, does it rain? This is the unknown variable, and if it rains, rain's probably 0.6, and so this means that if it rains, yes. So you follow this branch here, so you decide to go ahead with the party, and it rained. So the end, this leaf of this tree here, is the utility of that sequence of decisions and things that happened, the random variables which actually became instantiated on a particular path. Right? So this is minus 100. Similarly, here you say, well, I decided to go to the party and it didn't rain, and the utility of that is, say, 500. Okay, so these end nodes here are just these leaves are the utilities of the events along the path, the cumulative events along the path. So these are 4 outcomes, and then you could say, well, how do I sort of solve this decision tree, this tree of decisions? How do I map this back to the calculation before? Well, effectively, what's going on is that, well, let me just tell you what these things are called first. So these variables here, these are square variables, these are called decision variables. These sort of oval variables here, these are called chance nodes or chance variables. So we've got decision and chance nodes in a decision tree, and we've got these corresponding utilities. So we'll typically write these utilities on the right as much as we can. Okay, so yeah, so let's ask, how do we think about solving this? Well, you could say, one way to think about it is say, well, look, I don't know what's going to happen. I want to sort of find out what's the sort of, expected utility here at this node. Well, basically what this means is that, I could sort of, because I don't know what's going to happen here, this could happen, it could rain with probability 0.6, so the expected, not rain, well, if it rains probability 0.6, I get minus 100 utility. So if it doesn't rain, and I get 500 utility, so this sort of the expected utility of this node here is the sum of 0.4 times by 500 plus 0.6 times by minus 100, which is 140. So the idea is you're kind of working back from sort of the known things, the utilities, you're working back to what would be the utility then of that chance node. So this corresponds to the expectation computation that we did before. Computing the expected utility had then on a certain situation. And you can do the same for the bottom branch here. So the utility, expected utility then of this variable here is 20. So now you need to take a decision, which of these two to do. Well, if I basically find the larger of these two values here, then I should go to the max of those two things, and I put into here then the decision of the utility of the most likely of these child nodes here, the most useful, the highest utility for the child nodes. So what's going on is that if you've got a chance node here with two children, say, or a set of children, you need to compute the expectation, what you place into this decision, this chance node is the expectation of the child nodes. Okay? We do the same here, and for a decision node with chance children, you take the max of those chance children, place that decision node, and you carry on working backwards from the leaves to the root of this tree. And that's the way to solve a decision tree. Okay? So this is nice, it's very powerful, and it enables you to, in principle, solve all kinds of complicated decision problems. Right? You could write it down, but it's one way to do it. So by the way, sometimes in exam situations, these I ask you to solve these kinds of things, so do get a little bit familiar with this. It's happened in the past, it may happen again. Let's look at a slightly more complicated example. There are lots of complicated examples today, but this is another scenario. So let's have a look at this one. So this is the party-friend problem. So the point is that now if you don't go ahead with the party, the point is you can maybe try and visit a friend. Okay? But the problem is that you don't know whether your friend is going to be in, and whether or not your friend is in depends upon the weather as well. Okay, so let's just write down what this scenario in a little bit more detail. So we've got the utilities as before. So if this is a party utility now, so there's no party in it, and it rains at 0, etc. So these are party utilities. Now, let's say that the friend that you could visit if you don't go ahead with the party, if it rains, the probability that he's in his house is quite high. If it doesn't rain, it's a good day, the probability your friend's going to be in is quite low. So I'm going to have a corresponding utility of visiting my friend. So I could say, if I try to visit him and he's in, that's good. That's fun. So I get 200. Not pounds, they're just numbers. It's terrible sometimes to quantify your all these things. If he's out and you try to visit him, it's bad. Right? So you say I lose 100 units of satisfaction. Okay, and say the remaining utilities are say 0 in cases. And I said that your total satisfaction utility is the sum of these individual utilities, utility of going ahead with the party and utility of visiting your friend. And the same question as before, should you now go ahead with the party? Bear in mind that you could possibly visit your friend and get some additional satisfaction if you don't go ahead with the party. Now this is where it gets a little bit complicated, so I'm going to attempt to now rotate the screen to do this. Okay, I don't know if you can see this very well. You're at a slight advantage. Essentially, you can turn your nose the other way around. So this is, the same as before. We've got this party. You go ahead with the party, yes. This is the kind of same things before. There's the rain thing. Whether it rains, yes or no, etc. So that's what happens if you go ahead with the party. Because if you go ahead with the party, you can't go visit your friend because you're busy with the party. If you don't go ahead with the party, the graph gets extended a little bit because it can rain again, yes or no. If it, say, rains, well, you can go and visit your friend. And if you go and visit your friend, well, your friend may be in or not, you don't know. And the corresponding utilities associated with that. Maybe not visit your friend, and well, actually, the utilities then are zero, doesn't really matter in terms of that you go ahead with the party. So visit your friends, there's no utility there. Well, not your friends yet. So then, similarly, you could not go ahead with the party. Your friend might be in or out. Similarly, you might decide, say, not to visit your friend, and sorry, not go ahead with the party, not go ahead with the visit, and so you're not going ahead with the party, decide not to do the visit. Your friend is in.
But you don't. It's supposed to be zero.
That should be zero.
Wasn't that from the previous slide where there's no visit? You got 50 if it was a day when it didn't rain.
Oh yes, that's right. Because sorry. So what's going to happen on here is that these. I forget this point every year actually. I should remind myself. But anyway. So the thing about that is that we think these are bear in mind that this is the total utility of both the party and the visit. It's a summed total utility. Okay. So the visit utility is 0, but the party utility is 50. Okay. All right. So we get this, we get this kind of object now, slightly more complex looking decision tree. And we try to solve it as before. Well, it's kind of easy because all we need to do, again, say start at say these two nodes here. We fill in then this value here. We sort of by just taking the expectation of these two utilities here. Similarly, we go over here, replace this with the expectation of these two, so we get 40, etc. Work backwards. We've got two values here, 40, 0. Take the max of those two, go to 40. Etc. Right? Until you work back along this tree, you get again the utility of the party is 50, which is the idea there is that that corresponds to this value here, which is that you should go ahead with the party. As before. So what I'm trying to impress upon you a little bit is that these graphs are getting a bit messy. I need to get a new laptop. Oh my gosh, and I must hope that it's special orientation. Let's see if we can get this. One of these has got to work. Okay. So that's fine, but you can imagine that if you've got what's going to happen here is that you see that the same kinds of structures in the graph are showing up all over the place. So this part here actually is a copy of this bit down here. And some of these bits here are kind of copies of each other. So you could imagine if you've got a sort of a sequence of decisions to take, not just two, but many more, what's going to happen is that you can have kind of in general an exponential number of leaves on this decision tree, right? All the possible outcomes that could happen. You have to enumerate all of them. But there's also a lot of copying, replication of parts of this graph on the different branches. So whilst this is very, very powerful, you can do pretty much everything with this. It's also kind of a little bit unwieldy when we get towards a longer sequence of decisions. So what we're going to try to do is come up with another representation which will be more compact and useful for a longer sequence of decisions. And that's what the influence diagrams are all about. So these were cooked up in the 1960s and 70s as a sort of, another approach. So they, in some sense, are the kind of a little bit analogous idea is that, in some sense, the decision tree is like an enumeration of all the possible states, a little bit like a state transition diagram in some sense. And the influence diagram is more like a belief network. Okay, now the tricky thing is that we're going to use the same kind of pictures to describe both of these things. This is awkward, I'm afraid. Okay, so so this thing now is going to look like a decision tree, in the sense that it's got these, ovals and it's got these rectangles, but it's not a decision tree. It's a belief network. Okay, so this is a bit fortunate, but hopefully you'll get the idea. Now, so the question is, what's going on with that party, friend, visit sort of problem? Well, essentially what we're doing when we're solving that problem is we're taking a sequence of operations. We are doing some summations, right? Then we backtrack to do some maxes. Then we do some more summations, and then we do some maxes. Right? So there's a sequence of max, so of sum, max, sum, max. That's what we do when we solve the decision tree. And in general, by the way, these orderings are not interchangeable. You can't do, say, interchange the maxes and the sums in general. Right? That's not going to work. There's a specific ordering in which you do that, and that ordering corresponds in the decision tree case to starting at the leaves and working backwards. So let's look at this mathematically. Well, actually, I could write down my distribution. I've got this probability my friend is in, condition upon whether it's raining, and there's a probability it's raining. I could actually collect this into here if I wanted to. So I've got my joint probability distribution. And I've got the whole utility thing going on here. I've got the utility of the party, the utility of the visit. This utility of the visit is basically, I could also write that down. It's like, well, I'm only going to get that term there if I don't go ahead with the party. Okay, so I've got some kind of complicated object here. So the mathematics, what we're doing is taking this total utility object here. We do this sort of sum of the friend variables, the max of the visit. In this particular case, I can take that sum, this term of probability of rain over here, because that's the amount of rain, the sum of rain, and max of the party. Okay. So that's the ordering that we do. So the fundamental thing to understand about this whole influence diagram decision theory framework is it's all about an interleaved sequence of maxes and sums corresponding to the points where you have uncertainty and the points where decisions will have been taken. Okay. Now we can write that down as well. Look, I've got a belief network, probably Frank and rain times by P of rain here. And that is this little belief network here. Frank and rain, P of rain. So I'm going to try to then write down the fact that I've got some decisions which are going to be taken depending on some of these variables in some cases. So I've got two variables, decision party, visit. Okay, so I've got some utilities. So party, visit again. Now I could say, well, the utility of the party depends upon whether or not it's raining and whether or not I go ahead with the party. Similarly, clearly, the utility of visit depends upon whether or not I do go and visit the person, whether or not it's actually my friend is in. It also depends on whether or not there's a party, because if I don't go ahead with the party, then this is anyway zero. So there are some dependencies there. Now, whether or not you decide to take to visit your friend depends upon whether or not it's raining. Right? Whether or not you go ahead with the party doesn't depend upon anything else. You just take that decision. So one way to think about this is that really this influence diagram is kind of trying to write down, perhaps in a little bit of an awkward way, but this sort of sequence of operations that we want to carry out. If you really get kind of confused with this, the thing to bear in mind is the only thing we really care about fundamentally is the mathematics, which is this ordering of these variables here. Which sequence of variables are you carrying out the max sum operation on? What is that? What is the ordering of these max sum operations? That's all that we care about. So there could be other ways to graphically represent that, but the influence diagram is one.
So
Okay.
the dotted line,
Yeah.
why is it dotted?
I draw a dotted line as what's called an information link. Other authors use different notations. I just do that to try to emphasize it's an information link. So there's no, it doesn't mean like, in a belief network, this link suggests it's a real dependency. There's some kind of functional dependency between these two variables here. There's no functional dependency between these two decision variables. It's not that this visit is a function of the party. So that's why I personally prefer to draw it as a dotted line. Just the only thing I'm denoting with that is that what it means is that you will have the information about whether or not you decided to go ahead with the party when you come to take the decision about whether or not it's your friend. So it's just specifying the ordering in which the decisions are taken.
Okay. And also just the rain variables just coloured slightly different. Does that mean anything else?
Yeah, what I'm trying to say there is that in this case, you will there are some variables which will be revealed to you as you go along in the decision process. So what this means here, again, and this is just my personal notation, other authors will not do this, but I just want to emphasize that when you're going through this process sequentially, what's going to happen is that even though you don't know whether or not it's going to rain a priori, as you go along the process, it will be revealed to you whether or not it rained. Right? So in other words, when you come to to take the decision whether or not to visit your friend, actually you will know whether or not it's been raining. Okay, that would have been revealed to you in the future. A priori, we don't know it. So yeah. Okay, in this case here, I leave this one unshaded because actually we will never know in this setup whether or not our friend is going to be it, because we don't take any future decisions from that, so I don't need to shade that. Okay, so this is, just really stating that actually these dashed links and this shading is not standard, but I just want to try to reinforce that as an idea. So the partial ordering in this case, so this is kind of sort of less than sort of denotes some kind of ordering. And I'm going to put stars on variables we're going to maximize over, just for gain notational reasons to emphasize that. Again, that's not necessarily standard. So what this means is that the first decision we take comes before whether or not we know whether it's going to rain. Okay, and then when it's raining, we'll take a decision about whether to visit our friend, and then our friend will be in. Okay, so then when we think about the mathematics, this will mean, well, we'll start with this guy here at the end, and we'll sum over this variable. We'll max over this variable. We'll sum over this variable, and we'll max over that variable. Okay, so that's what all that we're trying to do, actually, really, is specify this partial ordering. And then we've got some other function, the belief networks, and probability, and we've got some associated utilities. And we just want to carry out the operations in that sequence. Okay. Yeah, okay, so random variables, X, they can be dependent on both decisions, functionally, and other random variables. And the utilities are just some deterministic function of either decisions and possibly also chance random variables. So one way to construct this partial ordering is to start first of all, say x0 is the set of variables which you know are they're given to you, they're observed already. So maybe somebody says, oh, I know maybe that it's gonna. Somebody says, I know it's raining now. So, or they know it's gonna rain tomorrow, something like that. Whatever that is, right? They've got some inside information. So those form your collection of variables which are already instantiated. Okay. And these are the things then that you know before you have to take even your first decision, right? That just fixed. So we could say x0 comes before the collection of variables d1. Set of decisions. I should probably read the calligraphic d actually. So what I'm trying to say here is that these are sets of variables in general. Okay, so similarly x1 are then the set of variables that are revealed to you before your second decision comes along. That will have been revealed to you as you go along through this process. Okay, they're not revealed at the outset, but after you've taken your first decision, a set of things will become known, namely x1, before you have to take your next decision. Okay, so this then, you carry on like this, and you get this partial ordering, such that at the end, these are the collection of variables that are never revealed to you. You'll never know what they are. Okay? So again, maybe another way to think about this is that the set of variable xk are those variables which are revealed between decision dk and your next decision dk as well. So the partiality here, what this is meaning is that when we think about this collection of variables here, we don't have any ordering within that collection of variables, within that set. So it doesn't matter. So for example, when you do the sum of the variables here, it doesn't matter which order you do that sum. Within the set, they are, there's no preference. Similarly, when if you had a set of variables d which contain more than one, then there's no ordering within that set as to which decision will be taken first. That's usually less common in reality. Normally you do have a particular ordering of decisions, but it could happen that you don't. Okay, so sometimes we, if we go back to this situation here, so this is saying, well, this is the information which this decision node, he knows basically when he comes to take his decision. So he knows what's happened in the past, he knows what's happened with this rain as we went along. But you can imagine then as we go along revealing more and more variables, essentially the information links are going to start filling up the graph because you know everything in the past. So in principle, this guy here is going to start cascading back to all past revealed nodes and decisions. Right? So this is going to get a little bit messy if we start to write down all of these information links. So there's a kind of convention called the no forgetting assumption that you kind of, maybe you don't need to write down all of these past connections for the information. It's just implicit in the whole influence diagram setup. Okay, so yeah, that's the no forgetting thing, but sometimes Okay, so these things are a little bit of a mess, actually, I have to say, but one way to try to navigate through this mess is to think that, well, basically if I take a decision now, it cannot influence anything that was revealed in the past. That wouldn't make sense. So what that translates to is that there must be a path connecting all of your decision variables. sort of so in this case there's a little bit of a poor example, but there's a path here connecting these decision variables. Okay. So there must be a sort of forward path going through your variables, which will always link them together. So let's look at an example, maybe another slightly complicated example, but maybe more relevant for some of you. Should I do a PhD? So there's going to be some variables here. So there's as part of your education, let's call E. So the E variable is going to be, do PhD or not. So maybe though it's going to cost you some money to do the PhD, so we're going to have a utility. C, some costs of doing the things, because it costs you some money, but also maybe lost income. But on the other hand, if you do the PhD, then maybe you can go on to greater things, and you might win a Nobel Prize. Okay, so let's say P is the Nobel Prize, whether or not that could be two states. Say you win it, or there's no prize or the prize. And that certainly, if you win the prize, Nobel Prize, it's going to be a big boost to your income. So we could say, what's the benefit, the utility, of the beneficial utility of going ahead with that? So there's a benefit there, and your income is going to go up as well. So we could say that the setup is that the domain of the education is do I do the PhD or don't I do the PhD? The domain of the income, let's say there's 3 states. So maybe you could have a low, average, or high income. The prize is whether or not there's no Nobel Prize or you win the Nobel Prize. So let's say the probability that if you don't do a PhD, that you win the Nobel Prize, say it's quite small. If you do a PhD, the probability to win the Nobel Prize is small, but it's bigger than if you don't do a PhD. I just made this up, by the way. Don't read too much into this. So then we can similarly complete the other probabilities. So similarly we could say, if I don't win the Nobel Prize and I don't do a PhD, that's kind of the worst of all scenarios. What's the probability you have a low income, no prize, and you do the PhD? Probability you have a low income is fairly low. Right? Similarly, say if you don't do PhD and you don't do prize, the probability you have an average income is quite high. Let's look at some other more exciting ones. Let's say you do a PhD and you win a prize, you can have a very high chance of having a very high income, etc. So these are again totally fictitious things. But let's say the cost of doing a PhD is minus 1. So this is the utility. So the utility of doing a PhD is minus £5,000, 50,000. The utility of not doing a PhD in terms of the cost to you is 0. And the benefit of your income benefit of having a low income, say, is 100,000. I think I must have been thinking about the US at this point. The average is a bit higher, 200,000, and 500,000 for having a high income. Okay, so given the totally fictitious numbers, though, the question is, should you go ahead and do a PhD? Because of course you don't know what your future income is going to be, and you don't know whether or not you're going to win the Nobel Prize. Right? So you have to take this decision now. You have to think about this. Is it really worth doing a PhD? So the setup is then the variables we have here are income and whether or not you win the prize. These are unknown, and you need to take this decision whether or not to do a PhD education program. So E star is before this collection is set here, chancellor. Okay. So this is the inference diagram. So So we've got income is a function of whether or not you win the prize, but also your education. Whether or not you win the prize depends upon whether or not you've been educated, right, done a PhD. The cost utility is a function just of whether or not you decide to go ahead with doing a PhD. And similarly, your benefits in terms of your income is a function of your income. The total utility is the sum of these two. So what we want to do is that the expected utility is going to be the sum over anything that we don't know. Right? So these are the things which come last in the partial ordering. P, or this is the probability of the whole thing for two variables. And this is the total utility here. So what we can do is then we can compute this for the two states of doing PhD or not doing PhD, and then find out which one is higher. And it turns out that if you do this for those numbers before, utility of doing a PhD is this, and not doing a PhD is that. So it's better to do a PhD. So this is kind of interesting, right? So this is we could write down a corresponding decision tree for this problem as well. And maybe it's a good exercise to do that. But this is the kind of influence diagram setup. So yeah, you can do more complicated things. So if you're interested in looking at these things, you can look at some of the demos. We'll focus through time. So this is a demo for the decision of whether or not to do a PhD. So this, you can write them down. The software does it all for you. This is the influence diagram over here. And there's a more complex scenario even than this one, where you can sort of. The question is whether or not you might then make a startup company at some point in the future. If you've got a PhD, it's more likely that you'll make a startup company, and whether or not it's successful, that will complicate the whole proceedings even more. And this is the scenario here. Now, I don't want to say too much about how to solve these things. And on one hand, all you need to do is to carry out that sequence of sums and maxes according to the partial ordering. It's easy in that sense. The question is, though, if you've got a very big influence diagram, is there a kind of an efficient way to carry out those processes? Is there some other way to kind of just formalize it in some way? And there is along the junction tree lines that we were talking about last week. And the only real difference is that basically this partial ordering defines what's called a strong triangulation. I'm not going to go into the details, but you can read them in the book if you're interested. And pretty much everything follows through as before. So that's the only real difference. And the software just does that. But that's not examinable. So it's just for your personal interest. Okay, so something which is more common is the Markov decision process. And this is a highly structured influence diagram. And it looks like this. So in this case, you've got some unknown variables. Okay. And you've got some utilities at each time step. And you've got some decisions you need to take. So in general, it says, well, at some time, I'm going to know, maybe what happened in the past. I need to take a decision upon that, and that's going to influence what goes on in the future. So this is the kind of thing where you might, let's think of a good scenario. Well, maybe I'll show you the scenarios. So let's say a maze, right? So you're in a maze. The question is, how do you, where you are in the maze now, influences, what you can do, what positions you can go to the next time. So the position, where you are in the maze might be this variable x at time t, right? There might be some states that are there. You can decide what turn to make in the maze. If I decide to go left or right in the maze, that will then determine where you are in the maze the next time step. Each time, though, where you are in the maze, it might cost you, say, some money to be there. Every time you're in the maze, it might be that some positions in the maze are good. Maybe if you're in the exit stage of the maze, that's very good. You have a high utility. If you're in a kind of the bear trap part of the maze, that's really bad. And you'll lose, say, lots of points there. But then the question would be, say, if I know where I am, say at the start of the maze, how do I take a decision? What is the optimal utility? What would be the sequence of decisions I should take such that I'm going to have the least total cost of going through this maze? So that's kind of a kind of scenario that you might like to think of in terms of Markov decision processes. Okay, so this it defines a sequence of an ordering variables, and we've got our probability distribution here, which is just a Markov chain. This is a probability of all the variables. Say maybe we assume that we're given, say, the first variable, say x1. I've got this sequence of decisions d1 due to dt minus 1. I've got this corresponding utility of all of the path, which is the sum utilities along the path. So u of x1 is the sum of all these individual utilities. And we want to find out that decision d1, what should I do right at the start now? And which of these options should I take in order to sort of ensure that in expectation in the future I will have the best sort of maze experience? Right. Well, you calculate this expected utility by doing your interleaved sum of sequence of sums and maxes. Right. So then you figure out what that is. Each of the two or however many states there are of your decision d1. And then you would take that decision which maximized the utility of d1. That's what you should do. Okay. So the question then is there a way to structure this, say, sequence of computations which is not too painful? Because if we were to write it down this way, it can be done, right? You could say, well, this is just some easy thing to do. I've got some object over here. I need to carry out this sequence of sums and maxes. It's easy, right? But the problem is that just to represent this object here, let's say these variables are all binary, the x's. There is an exponential number of states here of this table to store. Right? There are going to be 2 to the power t, roughly speaking, objects in this to store in this quantity over here. So it's totally impractical to do that. Cannot be feasibly carried out. So the question is, how to do. There's an influence diagram which is how we structured. How do we carry out the sequence of operations efficiently? Okay, so bear with it. It's kind of important, this stuff, in the sense that it's really a very important area of science. So hopefully you'll get the motivation, and we'll show how to fly a plane with it in a minute. And if I can find the demo, we'll show how to figure out how to invest your money. Okay, not knowing for sure what's going to happen with the stock market in the future. So there are many practical applications of this stuff. So let's look at a simple, smaller scenario. Let's look at this particular scenario, right? There are 4 variables. I'm going to assume that x1 is given. Let's just say some fixed state. And I need to take the sequence of decision d1, d2, d3, and not knowing what x2, x3, and x4 are yet. So we need to do sum of x4, max over d3, sum of x3, max over d2, sum over x2. That's what we need to compute. And this is our distribution here, Markov chain, and this is our total sum utility. So what we can do is the same as before. It's the whole how do we distribute our operators over these quantities as efficiently as possible? So we try to do that. We try to push everything as far as we can to the right. So we recognize here that this, where does x4 appear in this whole thing? Well, clearly it's here. So in these terms here don't depend on x4, so we can bring them out towards the front. And similarly, this two here, they don't depend on x4, so clearly that's going to be down there. Because when we did the sum over x4, that would just sum to 1. So okay. So I'm skipping some stages here, but hopefully by this point you're familiar with it. So just in your brain, sort of multiply this term here with this one and this one, right?
Yeah.
Carry out the sum over x4. What will happen is that this term here sums to 1. It will just disappear. So that's what I'm doing here. I'm just jumping to that point there. Although for this one here, that does depend on x4. So what we're going to have to do is we're going to have to take that sum over x4 multiply by u4. And now I want to do a max over d3 of all that. Well, actually, these two don't depend upon d3. So again, that max it just vacuums there. But this term does depend upon d3. So I can do that. So that first sum and max of the consequence of what's happened is that these two get copied down here. I got rid of the first term, but after just then, this u4 term got replaced with this term here. That's kind of good, right? Because it sort of suggests graphically there's some kind of analogous message passing, tail biting sort of sequence going on here. So we could say, well, let's call this thing here, whatever that is, that's a function now, though, of what? Well, it's a function of x3. Because we've done a sum over x4 and then the max over d3. What's left? Well, x3 is the only thing that's not being operated on. So that's some function of x3. And I could call that, if you like, a message from 4 times step 4 to times step 3 as a function of x3. And similarly, if I like, I could say, well, I could then collate this original utility on x3 with that information coming times step 4, that message, and I could call that, some other thing, notation. I could call that, say, b of x3, which is the combined existing utility plus utility from the future of x3. Okay, we'll typically call that the value of x3. Okay, so now that's nice. So that we can now we've reduced the computation. It's a limited cost to now this thing here. The only thing that's happened is that I replaced that with b3, and I got rid of the first 4 term. And then we can go on as before and distribute the sum of the max, and we're defining a new value for x2, which is the original utility for x2, plus this message coming from the future, where now that though is a v3 for the future, not a u3, right? Because that's data utility. And then similarly, the utility for d1 is just given by a simple expression for v2. So the important point here is that clearly what's happening if you had a long sequence in this Markov decision process, is that each of these operations carrying out, starting from the end and going along, is going to give us a linear time cost, where times the number of sort of nodes in this Markov decision process. So rather than being exponential in time or storage, it's just linear in both. So that's the big advantage of doing this. And this is called dynamic programming. So this is what Bellman did in the 1950s. When he sort of thought about this problem, he realized that he could structure it this way, the computations. And this is the origin of the term dynamic programming, which we have been exploiting previously in doing inference, and is a kind of generic sort of term for how to distribute now these operations over some. Okay, so Bellman's recursion or equation then is that there's a couple of ways to write it down. So one way is to define these utilities. So the utility from going from time step t to time step t minus 1 as a function of the variable x time t minus 1 is basically the max the sum of your kind of utility in terms of t plus utility coming from the future time, etc. So this is just a generalization of the formula that we were writing down before. It's more common though in textbooks to define everything in terms of the values. So the values of the utility plus the future expected utility. And you start at the value of the end time point just with your actual expected utility, because there's nothing coming from the future. So just that's your initialization. So just under this thing, we can just plug this definition into the original recursion there. We get a completely equivalent recursion, which is that the value at time step t minus 1 for this node is your existing utility plus the sum max over the future value. And you just initialize that recursion with v at time. At the end time is just your utility at the end time. Okay, so then you carry out this sequence operations down to the first time step, and then you can carry out finite, for example, your first optimal decision is just given by whichever it gives you the highest value at x1, x2, actually, whatever it is. Sorry, in this case it would be the expected value for, depending on whichever d1 gives you the highest expected value, and analogously, the general case. Okay, so that's kind of nice, right? So it says that even though I don't know what's going to happen with this maze, I can figure out what the best decision would be to take. Yeah. So let's we're going to do one slightly more complicated thing before I show you the demos. Okay. So let's say that you want to extend this, and you say, well, I don't really care about finite time. Maybe it's unnatural for me to think that there's a finite endpoint to this process. I just want to keep doing things, with no sort of finite horizon in mind, just adding finite time in the future. But there's a problem with that we, in general, are not going to be able to bound this set of infinite utilities summed up together. Right? That's going to be unbounded. So we need to address that in some way. So one way to do that is to say, well, actually, let's introduce this, discounting factor gamma, some number between 0 and 1. And let's say that also all of these utilities are themselves bounded by some maximum value, say u star. So none of them could ever be bigger than u star. Okay. So what I'm going to do is I'm going to replace this summation here by a discounted summation. That the utility of being at this point t times this in the future is gamma to the power t times by the existing utility. So what's going to happen is what this means is that if gamma is, say, very small, say 0.1, this means that I'm going to care much more. The utility of the whole path is much more dominated by the utility of near future events. Because I'm going to have the utility of the path is going to be 0.1 times by the utility the first time step into the future plus 0.1 squared times by utility the second thing in the future plus etc. And when you get down to this points for large t, these become exponentially small. So your decision will be that you will take your utility, and your decision will be that which actually says, well, okay, I do care about the future, all of it, but I care more about the immediate future. Okay, so yeah, this gamma then enables you to bound the total path sum to be finite. Okay, because you can say, well, if each u of xt is bounded by u star, then you can just do that, right? And this is then just a geometric series which you can sum. And as long as these gammas are less than 1, then basically, in the limit that t goes to infinity, this term here will become 0. And you're just left with the whole infinite time sum is bounded by this quantity here, which is finite. So this is a trick to do that. And the only thing we need to do is then to Bellman's equation works as before, but we just need to replace wherever we've had utilities. Just need to put a prefactor gamma. Okay. So the question is, do you want to have a break before we do the next bit? Because it's a little bit heavy, all this stuff. So let's have a break and come back to the half past.